In this lesson, EE301, we'll be discussing AC parallel circuits, or more specifically AC parallel elements. Just like when we were going over AC series elements, the major difference between DC is that we are dealing with continuously time-varying quantities for both voltage and current. And this is seen through the fact that we use the phasor notation in our calculations. Additionally, our resistances are now replaced by impedances, which are complex quantities having both a real and imaginary component. So the math becomes a little bit more complicated, but overall the principles remain exactly the same. And we see this right off the bat with our first formula, where we calculate the equivalent impedance for a set of parallel impedances. Everything looks just the same. We're taking the inverses of all these impedances, adding them up, and then we're taking the inverse of that quantity, giving us, again, that equivalent impedance. Also, just remember that this impedance is a vector quantity with both that real and imaginary term, which is usually denoted by bold, but I put the explicit vector notation there just to remind you. Also, like the DC, we have when we have two impedances in parallel, we have the familiar product over sum rule. And that just states that the product of the two impedances divided by the sum of those two impedances will give us the parallel equivalent impedance for those elements. Now, as you may recall when we were discussing series elements, when we had an inductor and capacitor with equal reactances, the resulting impedance was 0, which created a short circuit. Now when we have parallel elements and we have inductor capacitors that reactances are equal, the resulting equivalent impedance is infinite, which gives us effectively an open circuit. And we can see that right here, where we have this inductor with the positive reactance or impedance, and the capacitor with the negative imaginary impedance canceling out, giving us 0 in the denominator, which again blows up the value to infinity. So we have an open circuit. Alright, so if we move on to the current divider rule, again, all of the concepts from the DC side carry over to AC circuits. We're just dealing with phasor for current and impedances as opposed to resistors. So we see from the circuit right here, we have this current going in to these parallel elements. So if we wanted to solve for specifically one of the currents going through one of these paths, we would just set up our formula like so, where I1 is equal to I total times Z total over the impedance of that path, which in this case is Z of R. And we plug that all in and solve it. We get this, again, phasor quantity for our current. If we did the same for the other two paths, we would see a similar effect. And again, when we have the two impedances, the current divider special case rule still applies, where you have the impedance of the other path over the sum of both impedances times the total current gives us the current through the intended path. Okay? Just again, a note of warning, make sure you only use this formula when there are two impedances in parallel. It's a common pitfall for students to use this when there are more than two, and obviously they will get the wrong answer. And that brings us finally to Kirchhoff's current law. Kirchhoff's current law is just simply states that the sum of all the currents entering and leaving the node is equal to 0. So for the AC side, that just means that all of the phasors, right, the sum of all these current phasors entering the node is going to be equal to the sum of all the currents phasors leaving that same node. So in this case, right here, right, where we have this circuit, the way we have denoted it, we have this one current IFT entering the node. Right here, this is our IN, and we have I1, I2, and I3 all exiting the node. So if we want to solve for any given value, right, we can rearrange this formula like so. So if we wanted to solve for I of 3, we can rearrange our quantities, and we can use our current divider as well to solve. And that will allow us to get the answer for I of 3. So now that we've gone over the concepts for AC parallel elements, current divider rule, and Kirchhoff's current law, we'll go ahead and do a couple example problems. We'll start off with example 1, which is a pretty straightforward one. So if we need to find Z of t, right, this quantity right here, so we see we have 3 parallel impedances, and we'll take note that they only give us the reactance for both the inductor and the capacitor, so we have to make sure that we apply the positive and negative J for both of those quantities respectively, which will show that we have these 3 terms all in parallel. So we go ahead and rewrite this, plugging in our inverse values. So 1 over 200 plus 1 over J500 plus 1 over minus J460. And we take that whole quantity and raise it to the negative first power. Plug that into our calculator, and we'll get 200 ohms angle minus 2 degrees. And we'll do one more example. So coming down here to example 3. In this problem, it asks us to find total impedance as well as all of the current values, and then sketch a phasor diagram showing the phasors for our voltage source as well as all of our currents. So right off the bat, we'll take a look and inspect our circuit, and some things that stand out. They give us a time domain representation of our voltage source, and they only give us the capacitances and inductances for those elements and not the impedances. So we'll need to do a conversion there to make sure that we get the right values for our calculations. So first, we'll convert our voltage source into a phasor. We'll do that like so, right? So our phasor quantity for our voltage is equal to, we take the peak value right here and divide it by root 2, and then and we look at the angle, the phase angle within that time domain, and they don't give us any value for that, so that just means our angle is 0. And we can simplify this by writing 35.35 angle 0 degrees for our volt. Okay, now we solve for the impedance of our capacitor, which if we pull from our equation sheet is just 1 over omega times C. And then we also have to tag on this minus 90 degrees. And that's equivalent to adding a negative j to that value. Alright, so if we take a look at our time domain representation for our voltage source, we see that there's no 2 pi factor built into our frequency, so the value of 10,000 is omega and not f. So we can just go ahead and plug in 10,000 straight into our formula. And multiply that by capacitance right here, 1 microfarad, which is 10 to the minus 6 farads. And this gives us 100 ohms minus 90 degrees. Alright, similar process for our inductor, just a different formula. Alright, in this case we have omega times L, and we attach on a positive 90 degrees, which is also equivalent to a positive j. So using the same value for omega, 10,000, multiply that by our inductance, which is 20 millihenries, or 20 times 10 to the minus 3 henries. And that gives us 200 ohms with that positive 90 degrees. And with all of this information, we can now solve for our Z total, which is just going to be equal to 1 over Z of R plus 1 over Z of C plus 1 over Z of L, this whole quantity to the negative first power. So plug in our numeric quantities. 1 over 400 ohms plus 1 over 100 minus 90 degrees plus 1 over 200 ohms and a positive 90 degrees. Take all of that negative first power, plug this into your calculator, and our Z total will be 178.9 ohms with an angle of minus 63.5 degrees. Alright, now we can go ahead and solve for I of t using just Ohm's law, where we take our voltage and divide it by our total impedance. So we have 35.35, and our angle is, again, 0, and plug in the value for Z of t. And our resulting current is 198 milliamps at 63.5 degree phase angle. So the most straightforward way to solve for all these individual currents, I1, I2, and I3, is to use Ohm's law, right? Because we know the voltage drop across every one of these is going to be the same, and which is equal to our voltage source, E. However, you could also use the current divider rule, right, by dividing I of t into each one of these separate paths. But I'm going to go ahead and use Ohm's law. So for I of 1, I'm going to take complex E divided by Z of R, and that's 35.35 volts divided by 400 ohms, right? Since both of those phase angles are 0, I didn't need to explicitly state them, but to be thorough, it's best to do so. And my resulting current for I1 would be 88.4 milliamps. Then we have I2, same procedure, just put in C of C, and Z of C is 100 ohms with a minus 90 phase angle, giving us 354 milliamps with that 90-degree, positive 90-degree current, right? The sign has flipped, and this shows our current as leading, right? Current leads for the and this gives us this that gives us 354 milliamps with a positive phase angle, which is positive 90 degrees, right? The sign flips when we complete that division. And then finally we'll solve for I3. And Z of L is equal to 200 ohms with a positive 90 degree angle, and my resultant current through that path is 177 milliamps, and again the sign flips to minus 90 degrees. Okay, so if we draw a phasor diagram, we'll have I1 0 degrees, so it'll be along this real axis, and I'll put that right there. I2 is positive 90, so it's in the positive imaginary, and I3 inversely is along the negative imaginary. And IT, I total, will be the vector sum of all of these based off of Kirchhoff's current law, and will be, like we saw, it has a 63.5 degree angle So it's in the first quadrant right here. Obviously that's not the scale, but it gives you at least a kind of a conceptual representation of where all of those currents fall on the real imaginary plane. Yep. Well, that concludes this lesson. If you have any additional questions, please refer them to your instructor.